Hello, this is Mrs. Johnson. This is MAT221, Calculus 1. This is section 5.1, dealing with what's called areas and distances in Unit 5. Now, we just spent the last couple of days talking about section 4.8, which were antiderivatives. And in Unit 5, we'll see how we can calculate these antiderivatives and the significance of what they are geometrically as we move forward. So let's talk about section 1.5. Consider an object that we know is moving at a constant rate of change. Say we know that something is moving at 3 feet per second. Since we know that rate times time equals distance, we know that 3 times t will equal d in this particular case. If we draw the graph of the velocity, the distance that the object travels is actually equal to the area underneath that line. So if we think to ourselves, if we have a rate of change graph, so we're looking at a derivative graph, we know the derivative is a constant. It is 3 feet per second. That means if I drew this graph, if I had velocity in my output and time in my input in seconds, then 3 feet per second, if you notice, would be a constant function or a straight horizontal line. So we drew the velocity curve, which is actually not a curve, it's just 3 feet per second here. And we noticed that the distance I'm traveling is actually, we can interpret that geometrically by looking at the area between the rate of change curve, the velocity curve, and the x-axis. So we notice that if I move for 1 second, I know I've moved 3 times 1, or 3 feet. If I move for 2 seconds, then I know I'm moving 2 times 3, or 6 feet. And notice each one of these things will be equivalent to the area between the derivative curve, the velocity curve, and the x-axis. The area of that region gives us the distance that I've traveled. Or in other words, it's telling me about the antiderivative. If we're looking at the derivative, which is a velocity, this area underneath the curve is telling me about the distance curve, which I can't see. So after 4 seconds, I know that the object has moved 12 feet. Which makes sense because if I move 3 feet per second for 4 seconds, I've moved 12 feet. Now, Leibniz and Newton actually looked at these curves, and they started with constant curves like this and said, this is pretty interesting that I can interpret the accumulated amount of change in my distance function that I'm not even looking at by looking at the area between the rate of change curve or the velocity curve and the x-axis. So if velocity is not constant, Newton and Leibniz said we might guess that the distance traveled is still equal to that area underneath the curve. It's just the area is not so easy to calculate anymore. Because when I have a curved region, it's not so easy to just find what that area underneath the curve is, because unlike the first example where I had a nice rectangle where I could just do length times width, here I have a curve. Now the units will always work out, so Newton and Leibniz says this has got to be true. There's got to be a connection between the area underneath the velocity curve or the area underneath a derivative curve between the curve and the x-axis and the antiderivative curve, or the accumulated amount of change of the antiderivative over that interval. So if I give you this curve and I said velocity is equal to 1/8 t squared plus 1, we could estimate the area underneath the curve by drawing rectangles, touching the left corner of the curve with each rectangle. This method of estimating the area underneath the curve is called the LRAM, or the left-hand rectangular approximation method. We do this by drawing rectangles on the curve, touching the left curve at the left corner, touching the curve at the left corner of each rectangle. So what we're going to do is here, we're going to go up when the value of the function has an input of, in this case, t equals 0. I'm going to draw my curve. I'm going to draw up here and draw my curve so that the left corner of the rectangle hits the curve, and then draw straight across and then down for whatever unit I want to here in the input direction. In this case, I'm going by 1. But in order to find the area of this particular rectangle, I need to know what is the length and the height. What is the length and width of that rectangle I just drew? Now notice I'm drawing the rectangle so that the width is equal to 1, and I'm going to keep the width staying at 1 here for this particular example. My length is equal to the output of the curve when t equals 0. So when I put t equals 0 into the curve, that will give me the output of the curve, which will tell me the length of my rectangle. So the length of this rectangle is 1, and the width is also 1. Now let's draw another rectangle starting at time equals 1. Draw so that we're hitting the curve right here at time equals 1, and then drawing straight across for 1 unit. And when I do that, I need to know what is the value of the length of this rectangle. So the length of this rectangle, again, is the value of the curve when t equals 1. So I put 1 in here for t. 1/8 plus 1 is equal to 1 1/8. And then I could figure out the area of this rectangle. The area of that rectangle would be 1 1/8 times 1. And I could add it to this rectangle. So now so far these two areas added together would be 2 1/8. But I'm going to move across here because I want to go till 4 units here. So again, what I'm going to do is I'm going to go to the curve, and I'm going to draw a rectangle starting with an input of 2. I'm going to go up and hit the curve when the input is equal to 2. And then I'm going to draw across and then down so that my width of my rectangle is still 1 unit. But in order to find the area of this curve, I need to know what is the length of this rectangle. And the length of this rectangle right here is the value of the curve, the value of the function v when the input is equal to 2. So if I put 2 in here, I do 2 squared is 4. 4 divided by 8 is 1/2, plus 1 is 1 1/2. So the length of this rectangle is 1 1/2. The width of this rectangle is 1. So length times width simply is 1 1/2. And then lastly, I'm going to go to the curve. I'm going to draw a rectangle so that its left corner hits the curve with an input of t equals 3. And in order to find the area of this rectangle, I would need to know the length of this rectangle. The length of this rectangle is equal to the value of the curve when time equals 3. So I put 3 in here. 3 squared is 9. 9 divided by 8 is 1 1/8. Plus 1 is 2 1/8. The area of this fourth rectangle is 2 1/8. Now this is called an LRAM, or a left-handed rectangular approximation method, which makes perfect sense if you think about what it's saying. It's saying I'm using rectangles to estimate the area underneath a curved region using the rectangles, drawing the rectangles so that the left corner of each rectangle is hitting the curve. Now to find out what this value is, I would add these rectangle areas up. So that area would be 1 plus 1 and 1/8 plus 1 and 1/2 plus 2 and 1/8, which is 5 3/4 or 5.75. This is the approximate area underneath this curve, this velocity curve, for the first 4 seconds. It tells me approximately the distance that this object has traveled in those 4 seconds, approximately 5.75 units. Now, the only thing is we can definitely see that there's area that is not accounted for. This green area that I found is really an underestimate to the actual distance the object has traveled, because you can see some of that area has not been accounted for in this total of 5.75. So what Leibniz and Newton said is they said, well, what about if we change and do a right-handed rectangular approximation method, or an RRAM? This time, draw our rectangles so that the right edge is hitting the curve and then draw across. The right edge hits the curve and then draws across, and so forth. And when I do that, it will look something like this. Now notice I did this relatively quickly, but what I'm doing here is I'm really starting at the right, so I'm starting at 4, and I'm drawing up to the curve and drawing across and then down. Notice the right corner of the rectangle is touching the curve. Then I draw the next rectangle, hitting the right edge and then drawing across. Notice the right edge of the rectangle is hitting the curve. Same with the next rectangle, same with the next rectangle. And then I found out what each length times width is here. Well, the width of each of these is still 1. So I just figured out the length. So here when t equals 4, that would be 4 squared, which is 16, divided by 8, which is 2, plus 1 was equal to 3. So that was the area of this rectangle, this big rectangle. Then I found the area of this rectangle. That was the area, this length was equal to the value of the curve when time equals 3. That was 2 and 1/8. Here's this rectangle. The length of this rectangle was when the input value was 2, and the area of that would be 1 times 1 1/2, which is 1 1/2. And then this one where we hit 1, that is equal to 1 1/8. We get 7.75 units. Now, Leibniz and Newton also noticed that this approximation for the area underneath the curve is an overestimate, because we have area in these rectangles that is over the curve. So we would have an overestimate to the actual value of the curve. Now, averaging the two would give us a good estimate. Or Newton said, what about if we drew, another approach would be to draw rectangles so that we hit the midpoint of every rectangle is hitting the curve. In other words, if I want a width of 1, I would go here at 0.5 and I would hit the curve in the middle and then draw on either side, and then start here at 1 1/2 and hit the curve in the middle and then draw to each side, and then go to 2 1/2 and hit the curve in the middle and then go draw on each side, and then 3 1/2 and then draw on each side. So if I drew the rectangles would look something like this. Now notice when I'm drawing these rectangles, this is called the MRAM, which is called the midpoint rectangular approximation method. And it is the most accurate, for the most part, if I have a monotonic curve, or in other words, a curve that only increases or only decreases. Notice I found each length by finding the midpoint value of each of these values of input.